Welcome to Mind Shield. We protect the mind and pursue the truth. Let's get started.
Today, we are going to get real about brain signals. We're going to dive deep into the world of brain-computer interfaces and tackle those wild claims you hear about remote mind reading. But we're not talking science fiction here. We're going straight to the physics and the cold, hard facts. So let's start with the big question, the one you see in movies and all over the internet. Can some piece of tech actually read your thoughts from across a room or even through a wall? Is that even possible? All right, let's get into it. To even begin to answer that, we have to start at the source, the brain itself. And the very first thing you need to understand is just the incredible scale of the problem. We're not trying to hear a shout here. We are trying to catch a whisper inside a vault. Okay, so you know those EEG caps that measure the brain's electrical activity from the scalp? Well, the signals that manage to make it through your thick skull are measured in microvolts. That's millionths of a volt. It's an unbelievably tiny electrical signal. And if you thought that was small, let's talk about the brain's magnetic fields. They are even weaker. We have to measure them in something called femtoteslas. And a femtotesla is, well, it's a number so small, it's hard to even wrap your head around. Let me try to put this into perspective for you. The magnetic field your brain produces is about 1 billion times weaker than the Earth's magnetic field. You know, the one that makes a simple compass needle move. So just detecting that faint signal is a monumental challenge. So how on earth do scientists even attempt to listen to these tiny whispers? I'm going to walk you through the 3 main tools in the neuroscience toolkit. And you'll see, each one is pretty brilliant, but they all come with some pretty major trade-offs. First up, we've got EEG. You've definitely seen these before. The caps with all the electrodes stuck on. It listens for those tiny electrical signals, those microvolts, and it's fantastic for timing. You can see brain activity happening in real time, millisecond by millisecond. But, and it's a big but, the skull and all the fluid around your brain kind of smear and blur that signal, so it's really hard to tell exactly where the signal is coming from. Okay, next is MEG. This one measures those impossibly small magnetic fields. Now, because magnetic fields aren't messed up by the skull in the same way, MEG can pinpoint location much better than EEG. So what's the catch? Well, you need these incredibly sensitive detectors that have to be cooled with liquid helium to almost absolute zero, and the whole thing has to be inside a room that's magnetically shielded from, the entire planet Earth. So yeah, not exactly portable. And finally, there's fMRI. This is the one that gives us those beautiful, colorful 3D maps of brain activity. But here's the really crucial thing to get. fMRI doesn't actually measure the neurons firing. Nope, it measures blood flow. The whole idea is that when a part of your brain gets busy, it needs more oxygen, so blood rushes in. It gives you amazing detail about where things are happening, but it's super slow. We're talking seconds to update. It's kind of like seeing the scorch mark where a fire was, long after the flame is gone. So let's just sum this up. EEG gives you great timing, but the location is blurry. MEG has better timing and location, but you need a giant, ridiculously expensive shielded machine. And fMRI gives you a beautiful map of where things are, but it's not happening in real time. But you know the one thing they all have in common? You either have to be wearing sensors glued to your head, or you have to be literally inside a massive multi-million-dollar machine. Okay, so even with all those huge limitations, scientists are doing some absolutely mind-blowing things. Let's take a look at the absolute state-of-the-art of what brain decoding can actually do in a lab, right now. So check this out. In a landmark study from 2023, researchers used an fMRI and AI to basically decode the gist of what people were hearing in a story. The results were amazing, but you have to look at what it took to get them. The person had to lie perfectly still inside an fMRI scanner for hours and hours just to train the AI on their unique brain patterns. And here's the kicker. It only worked if they were actively cooperating. The second the person started thinking about something else, the decoding just fell apart. All right, so that's the best case scenario inside a perfect lab with someone's full cooperation. Now I'm going to pass things over to my colleague who's going to connect this all back to those wild claims of remote mind reading and show why they run up against what is basically a great big wall of physics. So let's flip the problem around for a second. Let's forget about getting signals out of the brain and just think about how hard it is to get a signal in.
This graph here shows how far a microwave signal can even penetrate into brain tissue before it just gets absorbed. And as you can see, we're talking about just a few centimeters at best. Your brain is actually really, really good at shielding itself.
So what you have to understand is this chain of failure that any remote device would face. 1, the signal starts out ridiculously weak. 2, it gets scrambled and muffled by your skull. 3, its strength drops off like a rock with every single inch of distance. And 4, whatever tiny little remnant of a signal is left is completely buried in all the other electromagnetic noise out there. Your Wi-Fi, radio stations, cell phones, power lines, you name it.
Honestly, this analogy just nails the signal-to-noise problem. It's not like trying to find a needle in a haystack. It's like trying to hear the sound of that needle dropping onto the haystack from a mile away during a hurricane. The physics are just absolutely brutal. Okay, let's put it all together now. When we actually weigh these extraordinary claims of remote mind reading against the stark reality of physics and biology, what's the final verdict? Well, it really comes down to this famous line from Carl Sagan: extraordinary claims require extraordinary evidence. And given the massive, compounding physical barriers we've just gone over, the claim that you can read someone's thoughts remotely through a wall, that is about as extraordinary as a claim can get.
So what does extraordinary evidence even mean in science? Well, it means a lot more than just stories or anecdotes. It means hard data that other scientists can reproduce in a controlled lab where you've ruled out every other possible explanation for what you're seeing. That is the absolute minimum standard.
And here's the ultimate reality check, something called a null model. Before you can say your device is reading minds, you first have to prove that it performs better than just random chance or a really clever guess. If your system can't consistently beat that simple baseline, it's not actually demonstrating a real effect. From a scientific point of view, it's just noise. It's not science, it's story time. So look, while covert remote mind reading is pretty firmly in the realm of science fiction for now, the real neurotechnology we do have is getting better at a shocking pace. We can decode the gist of what someone is hearing. We can help people who are paralyzed communicate. And all this progress leaves us with a really critical question for the future. As these tools get more and more powerful, where do we as a society draw the line between helping and hacking the human mind? It's a huge conversation, and it's one we all need to be having right now.